All right, we have one last lecture on special relativity, and I'm going to go out on a limb here and say that I think we're going to be wrapping this up shortly. I don't know if we're going to take the full time on this, but we'll see if that's the case. So the examples that I wanted to look at in this last lecture are to go back and take a look at some of the particle decays that we have looked at. So here's an example of a particle decay where I have something that has a mass, m naught, and it splits into two other particles. So one of those particles has mass m1, one of the particles has mass m2. Now, energy conservation tells us that the energy we start with will equal the sum of the energies we end up with. But this is not kinetic energy. So what happens in special relativity and what happens in reality, in nature, is that the energy we start with, if the starting object or the starting particle is at rest, then the energy we start with is mc squared of that starting particle. And the energies measured for the two decay products would be their total energies. So E1 and E2 include the mass and the kinetic energy of those particles. All right, so that's a statement of energy conservation for this two-particle decay. Now, momentum conservation also applies. Energy conservation requires us to use the total energy. Momentum conservation requires us to use relativistic momentum. Momentum as we understand, or we understand from special relativity, so the formulas are different from what we saw in physics 4a. So we're using energy and momentum conservation, but the formulas are going to work a little differently. Here is energy, here is momentum. Now, for momentum conservation, I'm just going to start out by writing down, look, if this object started at rest and it divides into two particles, each particle would have to acquire exactly the same amount of momentum, because we started with zero momentum and we need to end up with a total of zero momentum. So I need two particles with the same amount of momentum headed in exactly opposite directions. That's the way that would work. And so that's what we're going to plan on here, is to have particle 1, M1 and M2 heading in exactly opposite directions, and the magnitudes of the momentum will match. We're not going to worry about plus or minus signs here. The important thing is that the magnitudes match. Now, from the formulas we've written down, sort of the fundamental formula from special relativity for energy and momentum, we can square this, and then the squares of the momentum are equal to E squared minus mc squared. So I'm going to write that for each particle. E squared minus mc squared would have to equal E squared minus mc squared for each one of those objects. Now at this point, I am thinking, the formulas have too many factors of c in them. I'm spending so much time just writing down factors of c. What if I did a shortcut? Now this might sound a little dangerous. You guys can decide if you want to do this or not. If not, I completely understand. But to carry out the rest of the algebra on this example, what I want to do is every time there's an mc squared, I'm just going to write m. Now, what I will do is start thinking of m by itself having units of energy. With momentum, every time there's a pc, I'm just going to write that as p. And imagine that the p itself now is written in terms of energy units. So when I say mass and I say momentum, I really mean mc squared and pc. That way I don't have to write all the factors of C, and that will save us about half the time in carrying out the algebra. The dangerous side of this is that you guys have gotten so good at looking at equations and recognizing units, and when they look like there may be a problem, it may take some adjusting, but let's try this. So the first formula then would turn into m naught equals E1 and E2, and I'm thinking that m naught is in units of energy. So mass now could be measured in units of energy. For the formula here, I'm going to take out the c squareds, and again the formulas look easier, so I'm going to try this out. Now this is momentum conservation. What I'm going to do is remove E2 and replace it with m naught minus E1. That's just, my standard algebra, substituting one variable for another. I have two equations, two unknowns, and I just want to get one equation with one unknown so I can solve for it. When I do that and then expand this out, I see that the E1 squareds cancel, and when I solve for the remaining factor of E1, it looks first of all like this, 2m naught E1, and then it turns into this formula. E1 is equal to m naught squared plus m1 squared minus m2 squared over 2m naught. Now I can use a symmetry R, that's my first equation. I can go back and solve for E2 using a bunch of algebra, or I can stare at this problem and say, the problem is inherently symmetric. It was arbitrary that I called this object 1 and called this object 2. Any formula I write down for E1 and E2 needs to look the same if I switch indices. If I decide to call this particle 2 and this particle 1, the equations would have to look the same. And so I wrote down a formula for E2 by taking the top formula and switching all the 1's and replacing them with 2's, and taking all the 2's and replacing them with 1's. And that works if I have a symmetric setup in the formula. Now, as a way to check this, I know that when I add these two energies together, they need to add up to mc squared, or m naught, of the original object. So taking these two and adding them together, the m2 squareds cancel, the m1 squareds cancel, and I'm left with 2 m naught squared over 2m naught, which gives me m naught. So at least it's consistent. Actually, the formulas are fine. They're correct. And what we've shown is that there's a consistency here. When I add them together, they do add up to m naught. So there they are. There are the two formulas that we hope to come up with, telling us how the energy divides up between these two objects. Now I can take this a step further. What I can do is go after the kinetic energy formulas. So in addition to the total energy of the two decay particles, what I could do is, let's do this. I'll take the energy from particle 1, which we just derived, and now what I'm going to do is get the kinetic energy by taking the total energy for that particle and replacing it with, subtracting m1. So here is my expression for E1. Now to subtract m1 and keep a common denominator, I need to take that m1 and multiply it by 2m naught. So that's what I've done here, is I've given these two terms a common denominator. I've used this for E1 and then added some factors so that we can have a common denominator for the expression. What that has done now, this extra piece that we added actually can be combined with m naught squared and m1 squared to give us m naught squared minus m naught m1 plus m1 squared, which is a perfect square. And so I've taken it down to the next line and written this as m1 minus m1 squared. Now on the next line, what we've done is recognize that Here we have in the numerator the difference of two squares. So you're thinking, oh, this is great. This is like all the algebra I learned back in some algebra class at some point. What we're doing is we're multiplying things out and factoring things, and now we've got the difference of two squares. If I expand this out, it's going to be m naught minus m1 minus m2 times m0 minus m1 plus m2. So I wrote those out. This first term that we have right here, m naught minus m1 minus m2, that's the missing mass. When a particle decays into two other particles, the masses of the two particles are going to be less than the mass we started with. Mass is not conserved. It's energy that's conserved. So if we go back and look at the original setup, it has to be the case that m1 plus m2 combined are less than m naught. And the mass that disappears becomes kinetic energy. Sounds crazy, but those are the rules in special relativity. So the mass decreases, the combined mass is less than what we started with, and what's called the missing mass is converted into kinetic energy. So here it is. Right here, what we're going to do is take that missing mass and we're going to define that. That's what the three lines here mean. So we're going to define something called Q, where Q is the mass that disappears, the mass deficit, and that missing mass will equal the kinetic energy of the two particles. So I can substitute the Q into that expression in the numerator, and that says that K1 is equal to the available energy times this expression, and K2 is equal to the the total available kinetic energy times this. It's saying this. It's saying that Q is the combined amount of kinetic energy of both particles, and then the expressions here tell us how that divides up. Of the available energy, how much becomes K1 and how much becomes K2? Which particle gets more of the kinetic energy? Now, when we looked at total energy, if we go back and look at that expression, more total energy goes to the object with more mass. Once we take the mass out and ask, well, the object with more mass gets more of the total energy, what about just the kinetic energy? Then the statement reverses and says that it's the object with less mass that gets more kinetic energy. And that was true in classical physics too. Back in physics 4a, if I had two objects attached with a spring, one was 1 kilogram, one was 20 kilograms, and I let go, the 1 kilogram object ends up acquiring a much larger amount of kinetic energy than the 20 kilogram object. Okay. Anyway, these become our kinetic energy formulas within special relativity for a two-particle decay, and it tells us how the fractions divide up. So let's look at an example here. So I picked this example. There is a particle that is a heavy version of the electron. We looked at one already. There are three versions of the electron. There's the electron. That's the first version. There's a heavier version that's about 200 times as heavy called the muon. And then there's a version that's about 3,500 times heavier, and it's called the tau. So here's the symbol, tau minus, just like an electron minus, but the mass here is 1,777 MeV. That's a lot more than an electron. Electron's about half of an MeV. Now, the tau particle decays many different ways. There's, I don't know, 30 or 40 or 50. There's like 10 or 20 common decays, and then when you include the less common ones, something like this gets included. There's a particle called the K1, which has a mass of 1270, and the tau decays into its neutrino, and the K1 gets generated. Now that's not stable, it does further decays, but this particular decay, for whatever reasons, this came up randomly. I was looking at different decays, and I came across actually my dissertation from graduate school, and this was one of the measurements that was done in my dissertation. So this is actually a measurement that was first done at the Stanford Linear Accelerator Center within my collaboration, the TPC 2 gamma collaboration. And this was one of the topics in my dissertation, was measuring a couple of these decays, as well as kind of a comprehensive set of measurements. So I thought I would pick this out and just see how much energy these two particles are going to acquire. Now, if we generate the taus so that they are at rest, so we're looking in the reference frame of the tau particle, and the tau decays into these two different particles, what we can do now is ask, what are their masses? Well, that's given. So the neutrinos are basically massless. We can approximate those as 0 MeV. The K1s are 1270 MeV, so I know the masses. And notice that I've left out the factors of C here, and I'm using that shortcut approach. In addition, well, let me say this again. Knowing the three masses, knowing the mass we start with and the masses of the two decay particles, we can determine how much energy goes to each particle, how much kinetic energy each of the two particles will end up with, and how fast they'll be moving. Now, we have a real asymmetry of the masses of the two particles. One's basically 0, and the other one is actually pretty large. It's a large portion, but you can see there's missing mass here. There's like 507 MeV of missing mass, or mass deficit. So let's just practice our formulas. So I just plugged in values for M0, M1, and M2 into here. I didn't worry about the factors of C because the masses are all given in terms of energy units to start with. Plugging everything in and carrying out the calculations, I got that the K1 picks up 1342 MeV of the total energy, and that the neutrino gets 435. So, as we saw before, the K1, the heavier particle by far, picks up much more of the total energy than the neutrino did. Okay, so that was kind of step one, get the total energies. Now, notice that the Q, the mass that goes missing, the mass available for kinetic energy, is 507. Let's see how that divides up. So in this decay, we have this much available energy that's going to be released. It's going to be divided between the two particles. And so I'm just bringing out those formulas we had derived and putting numbers into them. Now, I did this, first of all, in terms of fractions of Q. So I solved these numbers. And what it showed was that the kaon, the K1 particle, its kinetic energy, was 0.143 of the total available energy released, whereas the neutrino acquired 0.857. So 14% of the available energy that was released went into the heavier particle, the K1. 86% went into the neutrino, which we're approximating as having no mass. In reality, it's got a small mass, but it's small enough we can approximate it as 0 for these purposes. Now, when I put the Q values in, what I found out is that 507 MeV gets divided up with 72 going to the K1 and 435 going to the neutrino. Now the last thing we said we wanted to calculate here was how fast are these particles going to be traveling. So now the neutrino in reality has mass, but we're approximating it as 0 mass. So within our formulas, that says that since we're treating the neutrino as if it's massless, we're going to end up saying the neutrinos are traveling at the speed of light. Now in reality, the neutrinos are going to be traveling at some speed just short of the speed of light, but I didn't look up masses for these. I guess I should have looked to see what the current best value measurements are for the mass of the tau neutrinos. Those are difficult masses to determine, but I should have looked that up to see. In any case, we can go in and use formulas from special relativity to determine a gamma factor for the K1, which worked out to be 1.057, and then use the velocity formula. There should be a factor of c here that I dropped. I apologize for that. But the velocity here then is 0.324 times the speed of light. So this is a handy formula. We'll use this from time to time. We'll see as, not only in this chapter, but when we get into nuclear physics and we get into particle physics, we'll see this formula used several times. And it's a good way to go in and build some familiarity with how energies get divided up in these reactions. Okay, now there's a couple other items, again, that I thought would be handy just to talk about. Nothing here that's required. Let me go back. This you want to know. So this derivation that we just carried out with particle decays, definitely take a look at this. I think there's some homework problems in the textbook where you can use this. And then there's also practice problems in the samplers, in the midterm resources, in the sampler exams. I've set up some problems where you can use those formulas. We've derived them now. You're welcome to write those in your notes. You don't have to re-derive them. It's worth looking at how we did derive them, though. Now, there's a couple of last topics here that you are not going to have to do homework problems, or there's not going to be a midterm problem on this. These are just some interesting questions that might be out there. One of the most fundamental things that we looked at in Physics 4a was if I push on an object with mass m, what are the accelerations going to be? And we said that Newton's fundamental laws of motion say that the acceleration depends on the force divided by the mass. And that became kind of the foundation for everything we did in mechanics, everything that we did in Physics 4a. Now we want to ask, what happens in relativity? Since space and time, we've learned, are different from what we thought they were. They're connected in a way that we didn't anticipate. That changes everything. So we know that once particles or objects are moving at high speeds, the formulas from Physics 4a, the classical formulas, can't possibly be correct anymore. In this case, these formulas, A equals F over m, would suggest that as long as we keep pushing on something, it will go faster and faster. Well, that contradicts special relativity's statement that there's an ultimate speed. There is, because of the way space and time are put together, there is no such thing as traveling faster than c. It just doesn't make sense given the structure of space-time. And so this can't possibly be the full story. It can only be a low-speed approximation. Now, we didn't derive this. I'm not going to go into the derivations. But what we can show is in special relativity, if we have an object moving in motion and we exert a force on it, in the direction that it's already traveling, the acceleration that we get is the force divided by gamma cubed times the mass. So what happens in special relativity is, if you continue to exert a force on something, you get less and less of a return on your acceleration. As it speeds up, you can keep pushing with the same force. So we can keep pushing on objects kind of indefinitely, but we get a smaller acceleration as they speed up. And eventually, as we approach the speed of light, gamma approaches infinity. So as you're approaching the speed of light, you can keep pushing on these objects, you'll get closer and closer to the speed of light, but you'll never cross that threshold. What's interesting here is, if, again, the object's moving in the x direction, what if we push on the object sideways? This is like circular motion. When we had circular motion, to maintain an object in uniform circular motion, we said we needed a centripetal force, a force that was perpendicular to the velocity. Well, in this case, the acceleration is the force divided by just one factor of gamma, gamma times m. Now that's interesting, I guess, that the acceleration formulas are different if we're thinking of components of the force and components of acceleration. I can look at the components of the force, x and y, and they result in components of acceleration that don't match up. What that would say is that special relativity says if I've got something traveling in the x direction and I apply a force at an angle such that there's an fx and there's an fy component, the angle of acceleration does not line up with the angle of the force. What we can say is that ay over ax is equal to gamma squared fy over fx. So that ratio of the accelerations does not match the ratio of the forces. In fact, what we can do is define an angle. What we can say is that the tangent of the acceleration, which is the ratio of tangent of the angle of the acceleration, which is the ratio of components, is equal to gamma squared times the ratio of the forces, which is tangent of the forces. So kind of interesting. We kept in physics 4a, kept driving home the point that the acceleration always lines right up with the force, that the components of acceleration will have the same ratio of the components of the force, and it's not true. Okay, they're actually shifted. For an object already in motion, the acceleration will not quite line up with the force if the force has components both in the direction of motion and perpendicular. Okay, so that's kind of interesting to see the resolution of, well, what prevents an object from going faster than light? That's because the fundamental formula for force and acceleration has factors of gamma included. Okay, so we picked up something from physics 4a. Let's pick up something from physics 4b. Back in physics 4b, when we were looking at electric forces and magnetic forces, we developed, look at these three formulas down here first, I guess. We had derived these formulas, which said that the electric force is on a charge Q in an electric field is given by Q times the electric field vector. If I break that down into components, that says the force in the x direction is Q times Ex, the force in the y is Q times Ey, the force in the z is Q times Ez. That wasn't so difficult, I hope. The magnetic force was more complicated. The magnetic force involved a cross product. Now, a cross product in classical physics becomes what we call tensor multiplication in special relativity. A tensor is a matrix. So in addition to physical quantities that are scalars and vectors, there are physical quantities that are tensors. And in the same fashion that in relativity, the vectors have 4 components. In relativity, the tensors have 4 times 4 components. They have 16 components. Now, there is what's called the electromagnetic field tensor that includes the 3 components of the electric field and the 3 components of the magnetic field, all packed together in one tensor, in one matrix. It's an antisymmetric matrix, which means the diagonal elements are 0, and of the remaining 12 elements, because it has elements that are symmetric and antisymmetric, that tells us then that of the remaining 12, there's only 6 independent components. So that's kind of interesting too. Anytime you encounter a cross product in classical physics, you know that in special relativity, it's going to be represented as a tensor, not as a cross product. So what we can do is we can take these formulas. This is a cross product definition from physics 4b. We can include a 4-dimensional vector for the force, time, x, y, and z components, and then we have to define a time component of velocity. So there's a rate at which we're traveling through time, which is the time velocity, and then the time component of force is actually power. So power and force are related in the same way that energy and momentum are related. So that kind of a unification there. And if I carry out matrix multiplication of this special relativity formula, it tells me what the forces will be. What we do is we create the force due to the electric and magnetic fields. Now, once we recognize that the electric and magnetic fields are part of the very same physical quantity, in special relativity, the formula looks like this. That's a representation of the force 4 vector, and it has an index. Now, in special relativity, indexes can be up or down, and again, you're not responsible for any of this. This is just giving you a bit of a peek into what happens when we start working in 4-dimensional space-time. The 4 components of the force on a charge depends on how much charge it has multiplied by the electromagnetic field tensor. So this now is a representation of all 6 components of the electromagnetic field. They're all part of the same package. And that's represented with 2 indices because I have rows and columns. So the mu's and the nu's in this formula have 4 dimensions to them instead of 3. And then finally, this last symbol is the 4-dimensional velocity, and this is just notation that tells us to carry out a matrix multiplication. Anyway, I thought it might be an interesting thing just to take a look at these last couple of examples, one very basic one from Physics 4a, and one pretty important set of force equations from Physics 4b, and show how they are modified within special relativity, and how special relativity unifies electric and magnetic forces into one force of nature. All right, I think that's it. So we finished that up within the allotted time pretty well. So this last slide is just pointing out special relativity has been around for over 100 years. Every prediction has turned out to be correct. There's just an overwhelming amount of evidence for special relativity. So, hey, it's reality, right? So we'll wrap up chapter 26 with that. And if you guys have questions, stop by office hours. We'll get those questions looked at.